and I'm going to take you through our lab today. So our lab today is on springs, and essentially, if you go in, I gave you, as always, the doc and the PDF. However, if you read it, you're going to see it looks super complicated. It's not complicated at all. It just looks super complicated. I built this off of someone else's lab, and the things that I'm stressing in here is actually useful data acquisition, meaning getting data that you can actually do something with. So our IO lab has a little eye bolt that you need to connect. That eye bolt connects to a force sensor. And when we attach a spring, specifically the long spring, to it, we'll be able to figure out how much force is being pulled on that spring. Forces, we assume in a really simplified manner that they're ideal springs. The spring force is always negative. It always acts against the direction you pull it. And there's something called equilibrium. And that means that for springs, we always measure from a point where if the spring's at rest, you're not pulling on it, you're not compressing it, that spring, the end of it is at zero. So we always assume that at rest it's at zero, and then we measure how far we stretch or compress a spring from that 0 point. You guys should know all this, but just to be thorough. Because the force is minus kx, where k is a constant that we find from a linear plot of data for force versus distance, which is what we're doing today, k equals minus f over x. So the spring force, it's a conservative force. That means we only care about the endpoints. It's path independent. Doesn't matter how many times you stretch. The only thing that matters is where you begin and where you end to determine how much the potential energy of the spring changed. That's equal to the work. And the potential energy of a spring, you should know, is kx squared over 2. All of that gives us that there's mechanical energy associated if you allow a spring to do work on an object. And that mechanical energy is the potential energy of the spring, kx squared over 2, plus the potential or the kinetic energy of the object. That should always be a constant if they are truly conservative forces. And we're assuming there's no height change, so we don't have gravity to worry about. So what we're going to do in this lab is we're going to take the IO lab, and I'm going to, well, the first thing I should say is you're going to need the mass. Now, we've done this a couple times. We've found the mass. I expect you to know how to find the mass. You can take the mass to be a constant, but I think we found it to be like 200 grams or something, whatever it was. I think mine was something like 200 grams. Whatever it was on a previous lab, just grab that and assume that that's your mass. If you want to redo it, you hold it by the eye bolt and you figure out what the force gauge is reading and divide by G. But you don't have to do the error analysis on that. I'll allow you to just assume that it's a constant and it is whatever you had. I want to say it's 200 grams, 0.2 kilograms. So go ahead and if you have it, open up your IO lab. One thing to remember is if you hit reset twice, it turns off everything. So make sure your IO lab's on. Turn on your wheel sensor, turn on your force sensor, get rid of velocity and acceleration. We won't need them. But right now, what we're going to do is hook up the long spring, not the short one. There's a short one and a long one. Make sure you get the long spring. I'm going to hope that you guys can barely see this. But with the IO lab on and not pulling on it, it says something about put it on a piece of paper. That's just to help you. But essentially, a piece of paper is 8 by 11. So if you pull it about the length of a piece of paper, it'll be pulled about 10 centimeters. What we're going to do is we're going to start it, and then we're going to lightly pull it to 10 centimeters. You might want to put this on something rigid so that you're not holding it in your hand. I've found that holding it in my hand seems to work fine. So once you have everything set up and ready to go, hit record, give it a second, and then just pull it about 10 centimeters. And then you can stop it. It doesn't matter if the data is all jacked up at the end. What we want is we now want to zoom in somewhere where it starts at about 0 and goes to about 0.1. And I can see that if I zoom a little bit more, that wasn't what I wanted. So I can go back, look for about 0.1 on the position, and then grab your data. I'm sorry, that's not what I wanted. Go to the graph one, make sure you start at about 0 and go to about 0.1. Hopefully, mine's not great, but hopefully your force graph is pretty much a straight line, a negative slope. And once you have that, this is where things are going to get a little weird. This is where things are going to get a little crazy. Make sure that you have your Excel open. Supposedly, and it doesn't work for me very well, but supposedly when you do this, there's a way to make it populate straight through to your Excel, but we're not going to do that just yet. So we're trying to get the data of the force and the position at the same time on a graph so that we can graph basically force over position, and the slope of that graph, if we put a linear trend line, will give us K. The problem with this is, if you look, your force sensor, it says 200 hertz. That means that it's sampling at 200 data points a second. The position sensor is only doing 100. We have a mismatch in our data, and that's really what I want to show you. So if you click on this little toolbar thing and go to export as a CSV, it tells me that it went to my IOLab work file export, and it's 1411114. So 141114. You might not want to write that down. I'm going to write it down because sometimes files get weird. Do the same thing for your force graph, and note that it's 141134. Okay, so now that I have that, I'm done with the IOLab for the moment. I now, on a Mac, I don't know where your files are stored if you're on a PC. On my Mac, they're stored in my documents. If I go to my IOLab work file and I go to my export, I can see that I have both of these. Now, if I go on the position sensor, that's the wheel sensor, I see all this weird stuff and it all says like zeros, and I recognize time, but I don't recognize much else. I would say, roll down, what I should say before I do that is your time and your cal 0. Time is the time, obviously. Cal is actually what our sensor is reading, and we can see that when we get to here. I don't really know what these are, but this cal 1 is our sensor. And what we want to do is we can see that this thing starts at, I don't know, a millimeter, and then ends up, if I scroll down in this column, at about 4.3 seconds, it's at 10 centimeters. So if I come back up, starts at about 2.38. So I'm just going to highlight from 2.38 down until I get to over a centimeter, or I mean over 10 centimeters. So I'm going to go to like 4.4. And I'm going to copy that. I'm going to open up my Excel, and I'm going to paste those. Now, when I paste these, what I suggest you do is write time and position. And then you can get rid of the middle file by clicking delete. We don't need the middle file. We do need to go into, this was our time and position. We now need to go get that force data. And the force data looks the same. We went from 2.38 seconds to 4.4 seconds. So on my time, I'm going to run down to 2.38 ish. So around 2.38. This is my force, this column. I'm not going to go back up, but column E is like a placeholder. I don't know what that column E is, but column F is your force and column D is your time. We're going to go to 4.4. So once I do that and I go to, I don't know, 4.42, I guess, copy that data, go back to your Excel. And what I do is I would just put it right here. And now comes the messed up part, the messy part. So as I said, they have different sample rates. And you can see that the time here is 2.301. This is 2.38, 2.39, on and on and on and on and on. Okay. So first of all, take this if it's not already. Let's go down and let's actually, let's go to 4 figures, let's say. So, hang on a sec. Where this ends. So I changed those. This lab will be due next week. It won't be due today. So you can go back and make sure that you understand this. So now that we have this, we can see that we have kind of mismatched data, which is not a good thing. But what we can do is we can kind of associate them together. And what I would suggest is start at whatever your first data point is. Here it's 381. And then go to the nearest, like the first one after, well, let's go with 2.4. I'm going to shift cells up. And then from here, I'm going to go to 2.6. So every 2 seconds. So I'm going to delete everything between 2.4 and 2.6. And then I'm going to delete everything between 2.6 and 2.8. And then I'm going to delete, well, let me go over here and do the same thing. 2.4 to 2.6. 2.6 to 2.8. Make sure you shift your cells up. And you can see that eventually 0 to 3.2, 3.2 to 3.4. I delete that one too. And I know this is really boring to watch. Sorry about that. Eventually, we will get to where our data man, I don't know why. Oh, never mind. It's fine. Oh, that's why, because I'm dumb. Sorry, I was being really stupid. Someone stop me when I'm being dumb. I forgot to get both columns. Okay. Make sure you get both columns. That's important. And all I'm doing is I'm deleting everything after the first data point that's every 2-second increment until the next one. So I'm deleting everything between 3.2 and 3.4 and on and on and on. Once I do this, I should be getting close now to where I want you to get it to 10 centimeters, which you can see I'm now at 10 centimeters. Do the same with this column. If you have a faster way, that's fine. But I'm going to actually get rid of everything before 2.4. Everything before 2.4 is all going away. 2.4 to 2.6. Almost done. I may need to flip my my data though, and I'll show you what I mean in a second. 2 more points. So I'm going to go to 4.4. Essentially what I've now done is I've made it so that my data is relatively matches in time. I can delete this column now, and if I believe I need to move position, I believe it's Y then X in Excel, but I always forget. Take your data and graph it. So insert a scatter plot. And that looks good. I can see that I have nope, I had that backwards. So I should have left it where it was. So it's X and then Y. I always forget that. Insert a scatter plot. And now I can see that I have X and I have F. The slope of this line, if I put a linear trend line, will be F over X. That is equal to K. The slope of that line is equal to K. Let's see what this K actually is when I insert this. I'm going to add a linear trend line. And your Excel or your Google Sheets or whatever you're using may be different, but I want a linear trend line. And I want the R squared value and the equation. So it's kind of hard to see the equation here. I'm going to change it to like 18, and I'm just going to move it. Always label things. So label your title, your graph, label your axes, all that stuff. But we can see here that the slope of this line is negative 11.902. And if we go back and we look at our force law is negative kx. So k, the slope, is negative f over x. And that means on my graph, my spring constant is 11.9. I have an R-squared value of 9991. That's really linear. The first question in this lab is like, is the spring law accurate? And if you have an R-squared value of almost 1 exactly, yeah, that is a linear force law. So that's all good. But we need the uncertainty associated with our slope. And that's a problem because we don't really have a way to get that. We could do it in some weird ways. We could go and we could get the standard deviation off the IOLab and blah, blah, blah. I don't want you to do that. I want you to learn something new in this. And you might have already seen this. I might have had to do it before. But if I haven't, we're going to look at this really fast. It's 4 minutes. Let me know if you can't hear it. But this is called Lin-S.
Today I'm going to show you how to do some quick and easy linear regression analysis with Excel. The first way of doing this is with the data analysis tool pack that Microsoft provides for Windows users. So
I kept the link. The link is in the doc version of our lab. You can just click on it and watch this. But essentially what this is something called, it's like a matrix. So you have to actually select it in a weird way when you do the function. And so pay close attention to how he does this. But you can see that when he gets this matrix, it's going to give him,
it's
going to give him the slope, the standard error in the slope, and that's what we want. If the slope is our k, SE is our error associated with our k. The rest of this stuff we don't care about, but just pay attention.
It's for Windows users of Microsoft Excel. I'm not going to show you how to use this. You might be able to figure out on your own. Another thing that you might be able to use if you're using the Mac version, which doesn't include the data analysis tool pack, is something called OatBran. I'll post a link to this at some point so that you guys can look at it and use it if you so desire. But I think the easiest and fastest way is using the line-st function. And I'm going to show you how to do that today. So I have some X and Y data here. And the first thing I'm going to do is select this data and generate a scatter plot. Now, this is something that you're going to be doing for your lab reports. You will need to clean this up quite a bit before actually including it in a lab report. But for now, I'm just going to show you how to add a trend line. So we're going to add a trend line of a type of a linear type. We're going to display the equation on the chart and display the R-squared value on the chart. And so here you go. So this is the linear regression analysis, but you'll note a couple of things. We don't have the error in the slope and the error in the intercept provided to us here. And so we need those for a lot of the analysis that we're going to do in PChem lab. And so we have to have a way of doing that. Now, the easiest and fastest way that I found to do this is with the line-st function. So what I'm going to do is I'm going to go over here and highlight this cell. I'm going to hit equals LINEST, parentheses open, okay, and this opens the function for us to start dealing with. And here are the things that have to go into this function. The first thing is the y values. So I'm simply going to select those and hit a comma to move to the next thing, which are the x values. This third thing is the constant. And basically, this is a parameter for setting your intercept equal to 0. We don't want to do that. We want to let the data decide where the intercept is going to be. So I'm going to leave that alone. And basically, I'll just put another comma in, leaving it blank up here in the formula. And that will set it to what it needs to be set to. We do want the statistics for the linear regression analysis. So I'm going to set this value equal to true and then close the parentheses and hit enter. Now what you'll see is that this gives us the slope. There's the slope, 1.6774, same thing here. Okay, now this formula, minus t, is an array formula.
So this is really important. You've done all that and you've entered your x, your y, your x, true. When you actually make or run this function, if you're not familiar with computing, you have to run this function. You have to execute this function. I believe it's control return on Mac. I don't know. I think it's Windows return on Windows. He'll tell us.
Formula, which is maybe a little different than you've used before with Excel. And the way these work is that I'm actually going to select a large section here, and this is comprised of 2 columns and 4 rows or 5 rows, depending on how you look at it. But this box here, and then I have to actually select in the formula bar here, and I'm going to hit Command Enter. As a Mac user, you would use Control Shift Enter if you're using Windows. And what this does is it automatically fills in all this data. Now here I've got a kind of a legend telling you exactly what each of these values represents. The first is obviously the slope. Second is the intercept. You can see it's the same as what we have from in our chart. Here we have the error and the slope and the error and the intercept. So this is the error and the slope. This is the.
So that's what we want. So I'm going to try and get it to work for me right now. I will say the last time I tried this, did not want to work for me. I don't know if it was my computer or what. My Y values are my force. So I just highlight them, put a comma. Then my X values are here. Put a comma, put another comma, and then true, and close the parentheses. I'm still in there. I believe he said Control Enter. I have a small problem with my parentheses. Control Enter, and hopefully, yeah, this is what it was doing to me last time. I don't know why it won't let me. I have some problem with my Excel where it's not allowing me to. Yeah, sure. Let me see if maybe this will work. Maybe I'm just not on the right. I don't know. If this doesn't work, I'm going to move on, and you can let me know if you're having problems with it. So that is my slope, 11.902. Don't know why. Well, I'll figure out what's going on. I'm doing something stupid, so we'll leave it at that. Let me know if you can't get it to work, and I'll go through it and try and get it to work once you get your data done. I'm sure it's something stupid that you guys will probably figure out. But that being said, once you have that, you'll have K, and you'll have from that second entry down on the left-hand column of the line est function, you will have the delta K. So that'll give you the squirrely delta K, which you'll need for doing the rest of this lab. So if there's any questions, let me know on that, using line S to actually get your error of your slope. I think it's a valuable tool that, as if you were paying attention, he mentioned that they do that in PChem. They're expected to do that in PChem. So if you're a chemist, you may want to know how to do that to be a little bit ahead. But it's actually nice to know how to get Excel to give you everything that, or at least the simplified error analysis tools that Excel has. So the next step that we're going to do is, now that we've calculated K, we needed to calculate K because what we're going to do is we're going to figure out if energy conserved in, or the mechanical energy conserved in our IOLAB spring system. How we're going to do that, if we go back to the IOLAB, is we're going to hit reset twice, get rid of this. You can turn on your velocity and position function. And then what we're going to do, we don't even need the force on. What we need is we need position and velocity. What I want you to do is I want you to, you can hit record before and then pull it to some point. I would really rather that you actually mount this on something because you're going to let it go. Okay. So pull it about 10 centimeters, let it go. And you can see that this was when I let it go. I'm going to zoom in on that. And we need two things here. We need two pieces of data, and I know this is not great data, but we need two essential points here. Let me see if I can actually do a better one. I want to do a better one. All right, that was iffy. Be careful, you don't damage your spring. So I can see here that I pulled it, I don't know. No, I don't want that. I want to zoom. I pulled it about, where am I at? I pulled it about 20 centimeters. Nope, don't do that. I pulled it at about 20 centimeters and then I released it. So this graph is actually perfect. I want to look at this right here. So I want to look at this region. And here's the only thing I want off this. I want where it began, and that's not great. So I want where it began when the velocity was 0. And I can see that the velocity is 0. I can choose highlight your data, and then you can actually look at this and see where your wheel position was by looking at your mu. So here, if I want, I can figure out what my my wheel position was. What I want you to do is essentially, when the velocity is 0, I want you to write down the wheel position. So take just a small gap. When you do that, assume that the error is the error associated with the actual value that it's given you. So on this graph, it's telling me that my position is 0.178 meters, 17.8 centimeters. My uncertainty is 0.001. I'm sorry, my resolution is 0.001 or 1 millimeter. And my error is half of that, so 0.0005 meters or 0.05 centimeters. That is the error associated with my position. That is delta x. Here, my velocity is not quite 0, it's 0.02. My uncertainty here is 0.0005 meters per second. Then, once it gets to 0, okay, I want you to calculate, and this is a little bit hard, but assume that this is 0. Remember that you're still going to have a little bit of uncertainty here, and you're going to have a small value, so close to 0. Record the final velocity. You can record it as a positive value if you want. It doesn't really matter because we're going to end up squaring it. So you're going to do 3 trials. Basically, pull it 18, 15 centimeters, hold it still for a minute, let it go. get the position and velocity when the velocity is 0, get the position and the velocity when the position is 0. And we're going to compare the energy at those two positions. I hope that makes sense. You're going to write down the position. So just take a very small section and just write down the mean and the mean for the velocity and the mean for the position. Call that the initial position for trial 1, and then do the same when it's at 0. And basically that's what I want. I want you to do 3 of those trials. When you do those, I want you to actually grab the graph of the position and the force. I'm sorry, not the position and the force. This was for the screenshot to go with your graph. This was it. The velocity, acceleration, position. You don't need the acceleration, but the position and the velocity, okay? And then what you're going to do is at the initial time, since you know K and you know M, and you've got an X and you've got a V, you're going to find the energy at the initial time when velocity was 0, and an energy at the final time when position was 0, okay? And once you do that, okay, you can do that, Ollie. So once you do that, I want you to take a picture of this, but essentially that's all we're doing. You're finding K by pulling it 10 centimeters, and then you have to manipulate that data to get that data so that you're only getting data points that are at the same time. You don't need a million of them, like 0.2 of a second intervals is fine, as I showed you. Find K with a linear slope. Find the uncertainty associated with K from linest. Then open it up with the position and velocity graph. Pull it about 10 centimeters and release it. Do that 3 times. Get the data when it's at a position when the velocity is 0, and at position when X is 0 and the velocity is maximum. Don't let it go too far. I essentially want you to get the velocity when it's at the equilibrium point, because, oh good, this is Ollie's data, and so he's got, his K is 11.9, or mine, or whoever said it. This is his error when he does the Linus function. So cool. So it's 11.9 newtons per meter plus or minus 0.11. And that's pretty good. Thank you, Ollie. That was helpful. I don't know why mine started doing something weird, and I don't know if my Excel is having an issue on my Mac or I need to download something, but it doesn't seem to want to do Linest for me. And I was hoping it was just me being weird the other day, but apparently it's still doing it. So what do I want from you? I want a graph of force versus X that you can show me that you got K off of with a trend line and with R squared value. I want a picture of the IOLAB data that you use to get that. Then on your data table. So for the data table, you're going to give me K and you're going to give me delta K. So this is just the slope of the linear trend line. This is from the Linus function. This is the mass from last week. If you really don't know it, use 200 grams. And then we're going to do 3 trials. And I want you to give me X will be a max, X will essentially be 0, and give me the change. And remember, that'll be 5 times 10 to the minus 4th for both of these probably. So give me V when X is at a maximum and V should be 0. V is at a maximum when X is 0 for each of these 3 trials. What you're then going to do is do this stuff. And you're going to basically, what I want you to do is for each of these, for trial 1 initial and trial 1 final, I want you to compute the mechanical energy. I want you to compute this term. Then give me the error associated with that energy. And so each of these terms is given to you here, as always. And then I want you to compute the difference between the final and the initial energy. Now, are they going to be basically the same. Well, they should be, but we have friction. We've already seen there's horrible friction in these iLabs on the wheels, friction on the desktop. There's things like this isn't an ideal spring, blah, 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 right? There's a million things that are affecting this. Air resistance might be affecting it. The angle, you might be angled weird. There might be some weird, something weird going on where you attach it, all sorts of weird things, okay? But when you get to the questions, does the experimental data support, and obviously all I want on the table of results is the initial energy with the uncertainty plus or minus as a percent, and the final plus or minus the uncertainty. So that part should be super fast and easy to do. What's going to be hard is getting the data and making it usable. And maybe you've never had to do something like this before. So if you haven't, cool. If you have, all right, well, then this should be fast. So help each other out in your lab or in your lab groups too. For those of you who haven't had a chance to do it, if you're going to go on to do research, you have to a lot of times do this. You have to clean up your data a little bit. So just know how to do it if you ever asked to do it, to make it look neat and nice. So the first question is, does the experimental data support the theory that a spring force is linear? All that means is R squared value of your graph should be close to 1. And I mean 0.99999, like mine was. I would say that my R squared value was 0.999. That means, yeah, that's a linear relationship between the spring constant and X and the force. From your measurement, did you conclude mechanical energy conserved? And that means just look at these percent differences and give them to me. Tell me, are they close to 0? Are they within 5%? Are they within 10%? Or are they ridiculous? Are they 30%? Which they may be. And then why? Why do you think it doesn't or it does? All I'm really asking you there is, do you think that you demonstrated conservation of energy with this experiment? I don't remember how good they got last semester over summer. I don't think it was great. I don't think it was horrible, but I don't think it was great. And I think the reason why is this is not an ideal spring, although it is close. It definitely changes the further it gets away. It's a little bit off. And I think the sensors on the iLab aren't great. I think they're a little weird. They're a little wonky. You have these little sensors and who knows, plus friction and user error and everything else. The last 3 questions are independent variables are the ones you choose. So you choose how far you stretch this spring. Technically, you could say that the spring constant, because you could choose a different spring, but independent variable is how far we stretched it. The fixed variables should really be the spring constant of the spring. We could probably change that doing something weird, heaving it up, I don't know. But I don't need you to get too crazy. The spring constant is assumed to be fixed. The dependent variables are what you measure. So they're the variables that depend on the initial conditions you create. And that was the velocity. That's what we're measuring. So independent, distance, fixed, spring constant, dependent, velocity. Purpose, I just want you to say, yeah, was energy conserved. State your findings, which means give me the percent differences for the different trials. Give me K. It doesn't say K on there, but you should definitely tell me what you found for K and the error associated with it. Where did the error come from? I don't want you to say, oh, well, maybe I don't know how to measure. I didn't choose the right point on the graph. I want things like friction, air resistance, not an ideal spring, anything you can think of that you would, if you redid this experiment, you would want to take into account and fix. Like maybe do it on a icy surface so that you know that the surface isn't having friction with the wheels. How would you improve it? How would you change it to make it more interesting? I know this lab's not interesting. This lab is actually super easy. I more want you to really concentrate on how to clean up the data and how to use things like LinEst. And so I didn't want this lab to be ridiculous and hard. And it's not meant to be. But definitely the person who does the graphing this week is probably going to have the hard job. So keep that in mind. As always, if you have questions on this, let me know. Are there any other questions about this lab that people have? If not, I want to go through homework 8. So, okay. Well, hopefully you find this useful for like chemistry and bio or any of your other labs you may have to do. Hopefully you'll get in there and they'll be talking about, oh, well, find this error, and you'll be like, yeah, I know, it's linest. I can do that. So hopefully it's useful to you and it's not just a busy assignment. But right now, what I'm going to do is actually, since I know some of you are going to want to take off probably, or go do your lab or whatever, I want to skip down to, if you've already done, I mean, in general, the people that come to the meetings and stay the whole time, they're on it on their homework. So I want to talk about 2 problems with torque that are very similar to problems that you will have on an exam, whether it's the next one or the final. And that is, we've already done these inclined plane over a pulley, except what happens when the pulley can move? If the pulley isn't massless, if it has mass, how do we find it? And what do I want to see from you to show me that you understand it? So in this problem, I'm going to imagine this is mass A and this is mass B, and this is a pulley, which I'm just going to call big M, MP. Okay. And I know the mass of my pulley is 4 kilograms, and I know mass B is, I'm going to put 20 kilograms. I'm going to make mass A really small because I want to make sure that it actually falls. And the radius of my pulley, and this is important, is going to be 1 meter, just for the heck of it. But now we're going to get into the fun stuff. And we'll say this is 30, I don't care. What we want to know is if this thing starts from rest and falls, how fast will A and B be going, and what will the angular velocity? So I want VA final, VB final, and I want the angular velocity of that pulley once B is fallen. Now, we know a couple things that we have to add here, but before we do that, I'm assuming that you all know how to do N for A, that this is MAG cos theta, that this is MAG sine theta, just the weight, and that there's a tension going that way. And we're going to assume that it's accelerating up the incline, that we've done this enough that we know how to do this. For B, I'm going to have the same thing. This will be the tension, this will be the weight of B. We've done this all before. A will be going down, Y will be positive down. But in the middle, I have a pulley that I have to deal with. What I want from you is a torque diagram. So I want you to do what we've already done, what we did in Unit 1. But then for the pulleys, I want you to draw torque diagrams. And how you draw a torque diagram is we're assuming, we'll get there. We're assuming at the center of the pulley, I have 2 tensions. Let's call this tension 1 and tension 2, or tension B and tension A. We'll come back to, they are the same tension, but we'll talk about that soon. Now we can see here, if we looked, we're assuming this pulley is rotating about its center. And notice it's rotating clockwise. That's super important. At a distance R, I'm assuming that tension A is pulling on this pulley tangentially. And at a distance R, I'm assuming that tension B is pulling down on this. So what I draw for my torque diagram is I draw a circle for the pulley, if I need to label it, and I draw R to tension A, and I know that they're the same R, but you'll see in the second example why I'm doing this. R to B, and these are 90 degrees. They have to be 90 degrees off because they're attached to the outer edge. R and T are 90 degrees. T is assumed to be tangential to the surface of the pulley, okay? So then what I need to do is I need to look at these two torques. And these two torques, if I put R and T together, tail to tail, I see that I have R and TA, and if I rotate, right-hand rule, rotate R to TA, if it's counterclockwise, that is positive. So I know this torque is positive, and this one is R and TB. And I can see by right-hand rule, that one is clockwise, so this one is negative. And further, I know that this whole thing is negative because it's clockwise. So what I've got on that torque diagram, this is the part that's important, okay? I draw my radius and I draw my tension. Remember that torque is R cross F, or RF sine. And remember that the sum of the torques is equal to I alpha. And remember that I for a disk is mr squared over 2. But all you have to write here is this. If there were 7 or 8 torques on here, you would write each tension and their radius and figure out, are they positive, are they negative? Remember that these diagrams allow us to write the equations right away. So we know for that first one, MA, X if you prefer, is T minus MAG sine theta. MAY, which was 0, is N minus MAG cos theta. And then we had MBA, I'm going to call it X because we already know that A and the X and AY are the same for these two guys, is MBG minus T. And we can put TA and TB, although we already know that TA has to equal TB by Newton's laws. They're a third law pair, believe it or not. But for now, leave them as TA and TB. Okay, so then we have our torque. We've already said that we write I alpha is equal to the sum of the torques. The torques are R cross F, RF sine. They're 90 degrees off each other. So this is RTA and RTB, or RATA minus RBTB. Why minus? The reason why is this one's minus, it's clockwise. But we also said that this whole thing was rotating negatively. So we have negative I alpha, RATA minus RBTB. This is a counterclockwise torque. This is a clockwise torque. So I hope you all see that that's why we write the torque diagram. What should be on the torque diagram is R and T and the sign of the torque. That way you can write this side of the equation really quickly. And then from there, what we can do is we use this guy. We also use that A is equal to R alpha in this particular case. We know that at this outer edge, A is equal to R alpha. For a circular disk spinning with alpha, at a distance R, right, A is equal to R alpha. So we can exchange alpha for alpha is A over R. We can exchange for, I'm going to change things back to R's. We can plug in for TA, MAA plus MAG sine theta. So this is MAA plus MAG sine theta. And we can plug in for TB. TB is MBG minus MBA, right? So MBG minus MBA. We can collect all the A's on the right-hand side, and we get MA plus MB plus I over R, all times A. If I multiply by R top and bottom, then they're all times AR, is equal to, moving this stuff over the other way, MBGR minus MAG sine theta. If you don't believe me, go through and just do that algebra and you'll see. But essentially, what I get here is that if I, oh, there's an R here too. If I divide through by R, this goes away and this, well, let me just erase them. If I divide through by R, I can see that what I have is I have the force dropping, MB, gravity's pulling it down, and it's being fought by the weight down the incline of A, right? So whatever force this is, minus the force that's trying to pull it the other way down the incline, all divided by the mass of the entire thing. Remember that I was mr squared over 2 of the pulley. So this is actually half the mass of the pulley because it can spin. And that's all you have. That's all you have to do. At that point, you could find that A is MBG minus MAG sine theta all over MA plus MB plus M pulley over 2. And you could find A. And then if I told you it started from rest, you could find V from the constant acceleration equations. And that's not too hard. We can make it harder by having maybe another mass in here. We could have friction. We can make this harder if we want. But the thing is, the new thing to deal with is this idea of a pulley and having tensions attached to a mass that can cause it to rotate. When I do this, I know that V final squared minus V initial squared is equal to 2A times Y final minus Y initial, or the height that it drops. And if it starts from rest there, so V final squared is 2 times all that junk up there times the height, basically, that it falls, which is easy to find. Once I find that, though, I said I wanted to know omega. Well, omega is at the edge, well, I'll just draw it. At the edge where these things are moving down with V, right? V is equal to R omega. So omega is V over R. And all I'd have to do is take the square root of all this stuff and divide it by R, okay? That's not too bad, actually. So you can find how fast a pulley spins because a mass drops and pulls it pretty easily. This is the other thing I wanted to talk to you about. So here, instead of them both being attached on the outer, one is attached to an inner and one is attached to the outer. This is a composite pulley. It's made of an inner pulley with, I'm going to say this is little r, and an outer pulley, which is big R, okay? And then I have a mass A and a mass B, and I'm going to call this mass 1 and mass 2. So again, if B is going to fall and A is going to rise, this whole thing's going to rotate negative. So let's flip that actually. Let's make it so that B is going up and A is going down, and then this thing's going to rotate that way. When I say composite pulley, I mean they're welded together. They both turn with same M1 and M2 have same omega, and they have to have the same alpha. That means, though, that MA and MB can have different velocities, very different velocities, right? So let's find if this thing falls from rest, just symbolically, really fast. We already know how to do A and B. Those two aren't hard. We'll call it just a tension, A, and we'll call this one tension B. And this time we do need to because they're at different radiuses. A, MAG, A. Okay. But now the torque diagram. And you can do this one of two ways. You could do it as 1, or you could do it as two separate pulleys. I don't really care. But for this A, it's the little r, and then the tension A is actually pulling down. You can move that over. I don't care if you draw it at the tip or if you draw it here, because you need to be able to rotate it. That is a right-hand rule, counterclockwise positive torque. So we have little r and TA, and that's going to give a positive torque. It's going to cause this thing to rotate positively. Here we have big R and we have TB, or we have big R and we have TB. And we can see that this is clockwise, so it's a negative torque. And our equation here is I total alpha, because they're composites. This is mr squared, this is m big R squared, m1 and m2. They could have different masses. So this is m1 little r squared over 2 plus m big R squared over 2 times alpha. That is equal to the sum of the torques, right, on all of them. So that's equal to R TA minus big R TB. Or what you could do is you could say I1 alpha is equal to R TA, and I2 alpha is equal to big R TB, and I1 plus I2 alpha equals RTA minus RTB. Sorry, I forgot the minus sign. You can do it either way. The point I'm getting at is with a composite pulley, you can add them later, or you can add them all at the same time. Have a good one, Eric. I think you'll be okay, but let me know. So what we've got going on here is we have basically the sum of the moments of inertia is equal to the individual, or the total moment of inertia is equal to the sum of the moments of inertia. So, okay, so once we've done that, we know that we have MA is equal to MAG minus TA. Solve that for TA. MBA is equal to TB minus MBG, because the acceleration is going the opposite way. So TB is MBA plus MBG, and I1 plus I2 times alpha is equal to RTA minus RTB. And so now we know that this is mr squared plus m big R squared over 2 over 2. Alpha is equal to R, so MAG little r minus MAA little r minus RMBA minus RMBG. And now, when we move things over, we need to get rid of either alpha or R. We can do it either way. We can either write each of these A's. So A, for pulley 1, A of 1 is little r alpha, and A2 is big R alpha. This was little r, and this was big R. Okay, or you could write that alpha is equal to, well, you can't really do that. You need to put these in terms of alpha. So we're going to do that with those. The reason why, we know that the acceleration on this pulley is equal to little r alpha, and the acceleration of this pulley is equal to big R alpha for the B block and the A block. So when we write that, we get M little r squared, m1 little r squared, sorry. Nope, m1, I was right. Squared over 2 plus mr squared over 2 times alpha is equal to magr minus little r squared alpha minus r squared mb alpha minus r mbg. And we're going to do more of these as we go. And then you can move everything over together. And when we do that, we get m1 little r squared over 2 plus m2 big R squared over 2 ma little r squared plus mb big R squared, all times alpha is equal to magr mb little r minus mbg big R. This will give you alpha, which will tell you how fast the composite pulley is turning. If you then wanted to know the acceleration of A, you would know that A of 1 is little r alpha, and A of 2 or A, B, is big R alpha. So you could find them. But essentially, what's the major problem here is they have different accelerations, and you somehow need to always couple them together. So here we couple them using alpha, because alpha is the same for both of the discs, both of the pulleys. But yeah, we're going to go through more of these. We're going to probably do one every class to show you a little bit more and more and more. But you're also going to get a few of these tonight for homework. So anyway, for the rest of this time that we have, I know we have 2 hours, but I'm not going to go for 2 hours. I just want to go over homework 8. There's a few little things that you may not know. And so I've got them all here so I can make notes for you. This one, it asks for the kinetic energy, and the kinetic energy is simply mv squared over 2. That's easy, and I'm moving on. But this one, this is a little bit different. We have 4 forces, or 3 forces, but we're going to turn one of them into a 4th force. Okay, great, Daniel. So force 2, make force 2 in the y and force 2 in the x. And I'm going to give you my actual notes on this, or my actual solutions to this later tonight. But we now have 4 forces. And this thing's moving to the left. It's moving a distance d is 3.01 meters in this particular problem to the left. Now, work is the change in kinetic energy, which means work causes energy to be gained if it's positive and takes energy out if it's negative. And that's equal to the force dotted with the distance. Now this distance is in the x hat direction, specifically the negative x hat direction. Any forces in the y aren't going to add anything to this. So we just need the forces in the x. So this is really force in the x dotted with dx. Now, we have a force 1 that it tells us it's 4.7 newtons. And we have force 2 in the x, which is negative. I'm going to assume that x is positive in the same direction as my displacement. So force 2x is negative. That angle is 60 degrees. So this is F2 times cos of 60. And 60 is half for cosine. So this is negative 8.68 cos of 60. That's negative 4.34 newtons. Okay, so I can see that F1 plus F2 is 4.71 minus 4.34 or 3.7, 0.37 newtons. That's the force. The work done is 0.37 times 3.01, assuming, I don't know where my calculator is right now. I'll try it on my stupid phone. 0.37 times 0.301, 0.37 times 0.3, oh, I'm stupid, 0.37 times 3.01. 0.37 times 3.01 is 1.1137, which is exactly what they got. Here's the important part of this problem, though. Is there a net transfer of energy to or from the trunk? That work is positive. The net force and the displacement are in the same direction, which means that we have a positive dot product. And therefore, this is Newton meters or joules, we're adding energy. If we're adding energy, the kinetic energy increases. Pretty simple. That one's not bad. This, they're actually using the magnitude of the work, but the work done against gravity. So the work of gravity is mgh initial minus mgh final. Okay, but they want just the magnitude of this. So if something weighs, mg of this roof is 290,000 newtons, and it's listed at a height of 0.20 meters, 20 centimeters. So you can find, we can assume that it's initially at a height of 0 and its final height is 20 centimeters or 0.2 meters. And therefore we can find the work and take the absolute value. This stuff isn't, that is another really simple one. Okay, so here, this problem is a little messy, a little annoying because of one thing. One really, really, really super annoying thing. If you tried to do this and you said, okay, the energy initially, well, first of all, we need to find K. And what it's telling us is if F equals minus Kx, K is minus F over X, but X is minus 3 cm or minus 0.03 meters. So we get a positive K, and F is 83. So K is 83 divided by 0.03. All right. Once we have K, though, the energy initially will be Kx squared over 2. And the energy final, we're going to assume is Kx final squared over 2. So the work done, they're telling us is 7 joules. But the work done by the block is negative 7 joules. It has to be negative 7. It says we then slowly move the block so our force does positive 7 joules of work on the spring block system. The block is then again stationary. So what we have is that the work is the change in E, which is, I should actually write negative, Kx initial squared over 2 minus Kx final squared over 2. And we know what initially it was. So we want to find X final. If we multiply through by 2 over K so that all these go away, we get that X final squared is equal to X initial squared plus 2 times the work over K. Okay. That's what's important. If you don't have this as a negative, this is going to end up being, sorry, this should be minus. If you don't have this work as negative for whatever reason, it gives it to you as a positive, but it needs to be a negative in the formula. And I don't know why they did that. but that's the way they worded it. And so your X final ends up being X initial squared minus 2 times minus 7 over, I think K is like 0.767 newtons per meter or whatever. But you're going to get a positive number in this term. You'll know that you messed up because if you don't have a -7 there, that term is bigger than the X initial term, and you have a negative sign under your root, which can't happen. So either that or they messed up and forgot that the spring energy is flipped, but I don't know. But for whatever reason, in this Wiley problem, they're saying that they move it slowly, so the force does 7 joules of positive work on the system. So yeah, that's what it is. This problem sucks in a weird way because it's a really cool problem and it's a really neat problem, but it's got something you might not have thought about. So this is pretty easy. We can assume that we have a mass, mg, and we know that it has 2 tensions. Both those ropes have tensions, but we're pulling down with this force. And here's where things are going to get a little weird. So it says here that it's frictionless. And we know that if we do this, we're pulling it, with constant speed. Constant V implies A is 0, and in the Y, MAY is 0 is equal to M, doesn't really matter, but 2T minus mg. That means that 2T is equal to mg, or T is equal to mg divided by 2. So the magnitude of F has to be the same as the tension. It has to be. F and T have to be the same. And if that's true, then that's F is mg over 2. And they gave you M, and you know G is 9.8 meters per second squared. Now, then it says to lift this, you lift it up 3.6 centimeters. So if I need to bring this up by 3.6 centimeters, and I need to bring this up by 3.6 centimeters, but it's stationary at this point, I actually have to pull down double. And if that's not apparent to you, you got to think about it. Because this side is stationary, as I pull, in order to pull it up, I need to pull it far enough up so that it doubles it. So on the free end, I have to pull that down a delta Y of 0.072 meters, 3.6 doubled. Now, here's the weird thing. So the work done by the force, is F dot D, where D is Y, is F times delta Y. The work done by gravity is mg times 0.036 meters, the height that we raise it up, and it's negative. But they end up being exactly the same. Why? Because F was mg over 2, and delta Y was actually double of that. So they end up being the same, 0.072. And you can see that right there, right? They are exactly the same. They're just negative of each other. It's a weird problem. It's a cool problem, fun problem, but they end up being the negative of each other. Another takeaway here. Yeah, I will. A little later tonight. I was writing them and made a mess of like 2 of them, and I ran out of time to finish them up so I could post them before class started. So here we have a block pulled up a frictionless. Bye, Cindy. Here we have a block pulled up by on a frictionless plane. I'm just going to go through these real fast so we can all get out of here. And I'll do the rest for everyone else. This problem, you have to figure out essentially the energy. So the energy at the top and the energy at the bottom. We're pulling it from rest to the top of this plane. So this is E2, and this is E1, and this is some block that's being pulled up. Okay, and we're told what the normal force is so that we can find the angle, because we know that the normal force is equal to mg cos theta, and we've been given mass, and we know the normal force. That's why you're given the normal force in this problem. And then we're told the displacement up the ramp. So once we have the angle, if we know that this is 2, the hypotenuse, and we know the angle, we can find y. Once we find y, we know that at the bottom to at the top, it's pulled up a frictionless force. So if the force dotted with 2, this distance, right? 2 times 53 is 106. This is 106 joules of work. But we've got to pull it up to the top. And at the top, it's going to have basically the force of gravity is going to do negative work, mgh, well, mgy here. And do I want to do this? I'm trying to shortcut this and I really shouldn't. So the work, sorry, I take that back. The work has to equal, this energy has to be mv squared over 2 minus mgy. If you don't see y, so the work is the change of energy, and our change of energy, we increased and we lost energy due to going up against gravity. The work done by gravity was negative, and we turned this work into kinetic energy. Lost them. Okay, so that's all you have to do. The weird thing that Wiley's doing to you here is they're giving you the normal force and the mass and expecting you to find the angle. And then you need to know that the work done by gravity depends only on the height. It doesn't depend on going up the incline. It depends on how high it rises. So you have to find the height in a couple of these. This problem got some people. So we have a block and we have a spring. And then we're going to drop it. And the block is initially at some h naught. If we assume that this is y is equal to 0, and then after it's compressed, okay, don't draw it like that. After it's compressed some distance x, let's call it, okay? So it's compressed some distance x. We have to find 4 different things. We're told that at the first time, x is 22.5 centimeters, and we're asked how much work was done by the block on the spring. So the force of the block on the spring is mg. No, sorry, take that back. The force of the block pushed it down, but it's kx squared over 2, positive. It pushed down on the spring, kx squared over 2. The work done by the spring on the block was kx squared over 2 with a minus sign. It took energy away from the block. So one way to think about this is kx squared over 2 is the amount of energy that got stored in that spring. That energy had to come from somewhere. The block put positive energy into the spring, collapsing it. The spring took positive energy out of the block by slowing it down once you dropped it. Basically, all of its potential energy became spring potential. Potential energy of gravity became spring potential energy. Then you can also find the value of H naught by knowing that it had mg H naught here, and here it has energy of kx squared over 2 plus mgx, okay, with a negative sign. This is a negative sign. Basically, it has potential energy of gravity and potential energy of gravity of both, and then it has the spring energy in there too. And from there, you can find H naught. The final thing is, how far would it compress if instead of H naught, it was 4H naught? Well, if we put a 4 here, noting that this is a negative, I'm just going to change it to there. This is a quadratic where this term is constant, and if you use H naught that you found in C, this is the constant, the C term. This, well, you would move it over so it would have a negative. This is your A and this is your B coefficient, and you can find it with a quadratic. It's not hard. The main thing to understand is that the energy, whenever there's a spring and it's vertical, the energy has mgh, it can have kx squared over 2, and it can have mv squared over 2. However, in this problem, there's no energy where it does have velocity. And then you just find the energy at different points. The other trick here is to make sure that you know that when the spring is at equilibrium, we're calling that y is equal to 0. And from there, everything else is easy, I think. Tarzan. Now, when he's at some angle, this tension in this rope actually depends on the angle. It turns out. I think it actually depends on the other angle. But if you do it, the point being that unless he's straight up and down, the tension has some component of sine or cosine multiplied by it. However, when he's straight down, the tension, mg, the tension is straight up. I'm sorry, I drew that arrow backwards. The tension at the top, when he's straight up and down. That is when the force is greatest. However, MA is MA rad because he's swinging, right? And it has to point up towards the top because it's radial. So this is T minus mg. And A rad, if you don't remember, is V squared over R. So we have the tension is equal to M A rad minus or plus mg, move that over. So the tension is mv squared over r plus mg. But how do we find v? Well, when he's here, he has mgh energy. And when he gets to the bottom, he has mgh plus mv squared over 2 plus mv squared over 2. But we assume that he initially had no velocity, and we assume that here h is 0. We're told he descends 2.8 meters. That means that this h was 2.8 meters. From there, we can set mgh is equal to mv squared over 2. That goes away. V is square root of 2gh. Plug it in there, find the tension. It's going to be less than the tension that the vine can exceed. So this is an energy problem. This is kind of a lot like the ballistic pendulum problem without the momentum part of it. This one, all you have to do on this one is note that initially height A is 0. We don't know what height B is. I'm sorry. Let me go back on that for a minute. Height A initial is 0. Height A final, I don't know yet. Height B initial, I can call 0 if I want. I can have a different 0 for both of these. Height B final, I was told after it's going to fall 20 centimeters. So I know that. Okay. And then what is the energy at any time? The initial energy of the system has to be MA GHA initial plus MAVA squared over 2 plus MBGHB initial plus MBVB squared over 2. This is 0, this is 0, and they both start from rest. The initial energy is 0. The final energy, now we know that they have to be traveling, if they're stressless ropes, they have to be traveling at the same velocity. So I can say MA plus MB over 2 V squared. I'm just going to combine these two final terms together, plus MAGHA final plus MAGHB final. And since this E initial is equal to E final, it's equal to 0. This is actually going to be negative because it fell. And this, I don't know yet. Okay. But I need to know it to find V final. So with this being negative, when I move it over, it's just a case of whatever. So now, how do I find how high HA rose? I need to find Y. Assuming that it started at 0, what is Y final? Well, I know this is 0.2. And I know that the angle is 27. And by SOHCAHTOA, okay, sine of theta is opposite over hypotenuse, or Y over hypotenuse. That means that no, that's not what I want. Sorry. I'm being dumb. Forget what I just said. That's not true. It goes up 2 meters. Because the rope gets pulled down 2 meters, it slides up 2 meters. So my hypotenuse is 2. So I need to find Y is hypotenuse of sine theta, which is 2 sine of 27 degrees. Once I know that, this is my HA final. That's how high it rose. And once I have that, I'm cool. I've got it. This problem is just an energy problem. Make sure you understand it, understand how to do it. This is a lot like something you would have on an exam, because you have to recognize that the gravitational energy depends only on the Y height, not on it going up the incline. This one is basically the same. You have work of friction now, and you have to find the angle. Remember that tan of an angle is Y over X, so angle is arctan. So you can find this angle right here. They gave you D1 and D2. That's your Y, that's your X. Once you have that, it's being pulled up at a constant speed, okay? This is what's weird. We want power, and power is change of work over change of time, but we're assuming that the change of time is 1 second. So we really just need to find the change of work to pull it up. Now, initially, the energy will be mgh initial plus mv squared. The final energy will be mgh final plus mv squared over 2, plus the work of friction this time. And the work of friction will be u mg cos theta delta x. We have to add this here. You could put it over here because, you know, force of friction is minus mu n. But if it's here, it's minus mu n. If it's on the other side, you give it a positive sign. I put it here because it's already happened at that point. We're told that we want the power after 1 second. How far has it gone up after 1 second? Well, if V is equal to X over T, and that's equal to 1.18 meters per second, then obviously the change of X is 1.18 meters. So you know what delta X is here. You have theta from there. You have the mass. You know G. You know mu. Mu is given 0.37. These go away because they are they are the exact same, we can assume that this was 0, right? So what is that final height? Well, you can find that because you know this is 1.18 and you know this angle, and therefore 1.18 sine of the angle will give you height final. That is your change of work, is mgh final plus mu mg cos theta delta x. And so what you end up with here is taking this and dividing it by 1 second will give you the power. But that's just doing the energy initially, the energy when it rises to the top, and adding some work for friction to the final energy. I hope that's not too hard to understand. Along those same lines, these are roller coaster problems. All you do is EA, EB, EC, and we'll get to ED in a minute. So this is mgha plus mva squared over 2, and mghb plus mbb squared over 2, and mghc plus mvc squared over 2. And we're going to assume that EA is equal to EB is equal to EC. We're going to assume that HB is 0 because it's at the bottom here. This is H1, this is H2. And from there, you can solve. They give you the VA, they give you H1, they give you H2. So you can, using just these two things are equal to MBB. So using MGH1 plus MVA squared over 2 is equal to M over 2 times VB squared. You can find VB from that. Then you can find VC, making sure that you add that energy term. Once we do that though, all of these, any of these, all right, EA is equal to ED plus work of friction. EB is equal to ED plus work of friction. EC is equal to ED plus work of friction, where the work of friction is mu n, which is mg, times some change of x. So we can see that once you find, I don't know, you could actually, here, we're going to assume that ED is mgh2 plus mvd squared over 2, and that's 0. So let's set EC equal to ED. Plus work of friction. So we would get mgh2 plus mvc squared over 2 is equal to mgh2, d and c are at the same height, plus mvd squared over 2 plus mu mg delta x. A few things first, these two terms go away. We assume that it comes to rest. We can get rid of the mass. So delta x is VC squared over 2 mu g. You're going to find when you do this that it's less than L. But this is just practice on doing energy with friction, with work due to friction, and where to put it, how it, EA is equal to EB is equal to EC because there's no friction anywhere here. All you do is write MGH plus MV squared over 2 for each of them, and then figure out if you know H or V, or solve for them. But when you get to D, you have to account for the friction that took energy out of the system, okay? So you, in a way, you could write EA is equal to ED plus work of friction, or you could write ED is equal to EA minus the work of friction, whichever way you see it. I don't really care which way you write it, but the initial energy is equal to the final energy at D plus the work of friction, or the energy at D is equal to whatever initial energy you had minus whatever work was lost to friction, whichever way you like to see it. Just remember that if we had like a further, if we had like it dropped again and we had some E point, the energy at D is equal to the energy at E. but the energy at D is plus the work of friction is equal to the energy at C. So energy at D is equal to the energy at C minus work of friction, which is also equal to the energy at E. You just have to be careful with where that work of friction comes in and goes out. It's not too hard, but it's easy to mess it up. This final one is pretty easy. Energy at the top, energy at the bottom. She slides down a pole. The energy initially and the energy final. First, there's no work of friction. So the initial energy is mgh plus mv squared over 2, and the energy final is mgh plus mv squared over 2. We're going to assume this is h is 0 at the bottom and h is 4.9 at the top from rest. And therefore we get that mgh is equal to mv squared over 2. M's cancel, v is root 2g over 2gh. If there's friction, however, so we have that the energy initially was mgh, the energy final was mv squared over 2, and energy initial is equal to energy final plus work of friction. And they gave us just a value, 460 for the friction magnitude. So we would get that energy final is equal to energy initial minus work of friction, or mv squared over 2 is equal to mgh minus 460, or v is square root of 2gh minus 460. And that's not too hard. So just make sure that you understand this stuff. Energy is always going to be with us, always. It's always going to be useful because it's easy to write down and you can find the velocity really fast. And hopefully when you get through these, you'll see that it's really just a matter of writing the energy at each point down. I know some of these have weird Wiley things going on, and I'm sorry about that. But any questions for those of you that are still here? I will post this handwritten, nicer than what I wrote here, later tonight for you, and I'll post another homework for you guys with some stuff on torques and rotating things. It won't be too bad though. It won't be like 12 questions. Yeah, it's a little bit of handful. You all right, Kevin? Cool. All right. Well, if you guys have any questions or you need me for anything, they're all in the book, Emilio. If you don't have the book, you should have the book. Do you not have the book, Emilio? Okay, cool. Yeah, it's so really chapter 9, you can look at those and go, oh, it's a collision problem. Or what's weird about momentum is you always have momentum. MV initial is equal to MV final always. And all those problems in 9 are all like momentum problems. So they're chug and plug. I mean plug and chug, which makes them pretty simple. And then it's just a tool we always have. We can always go, oh, well, I know the momentum's conserved. So if I find the initial momentum and the final momentum, I'm good. And you move on. What we're doing now in chapter 10 is we're doing this torque stuff where a force at some radial vector causes a rotation. And we need that for things going around. You guys will actually see it more useful next week, because we'll have, like, you probably never thought of it, but when something rolls on the ground, there has to be friction. And you're not dumb for not ever thinking that, but honestly, none of us really think about that if we can walk, there has to be friction. If there wasn't friction, there would be like ice. If there was no friction, there can't be a torque on you, which doesn't allow things to rotate. So for a wheel to rotate, there has to be a force of friction acting on it that allows it to rotate around. In order for this to rotate, it has to have a force pushing, you know, in this direction, which is weird to think about. And so we're going to talk about how friction actually allows you to roll down. It's probably easier to think of an object rolling down a hill has to have friction in order to roll. And then we can see that as a torque at a radius r, where F crossed with r gives you I alpha. And that's really the big takeaway from chapter 10, to be honest, is that there's all these things called moments of inertia for different types of objects, and that a torque causes a rotation. And that we describe that rotation with alpha, and we can relate alpha to r. I know it's a lot, it's a handful, but so for homework 8, all the stuff is in 7 and 8. For homework 9, it's in 9. For homework 10, it'll be in 10. Trying to keep the homework lined up to the chapter for you guys so it's easier to locate stuff. But anyway, whatever you guys need, text me, let me know. If you start working on this lab and this lab starts being weird or funky, let me know. I'm always happy to help. So hopefully you're doing okay. Hopefully your other classes are going well too. And I'll talk to you soon. Thanks, guys. Thanks, Tiffany.